So, the last thing we're going to do this week is we're going to learn how to compute the surface area of a surface of revolution. Now, we've talked about volumes of revolution before, right? So that's one thing, that's fine. Now we want to talk about the surface areas. And the reason we reserved this topic until now is because, once again, the integrals that we're going to get from this process are very frequently going to be not so nice integrals. Integrals that you really need some kind of sophisticated, by which I mean annoying, techniques to go through and solve. And so some of the time I may just ask you to set up an integral and not actually solve it. And as always, at this point, if you want to use like a table of integrals to help you with the solutions, then go ahead and do that, because these are going to be some fairly tricky integrals, just like doing the arc length integrals, really. It's the same kind of idea. So how do we find surface areas from a surface of revolution? Well, I'm going to start off by thinking about, let's suppose that we got, here's some A, here's some B, here's some curve, y equals f of x, and let's suppose that we spin this thing around the x-axis. We can really do this more generally, but let's suppose that this is what we're doing for now. So in this case, we end up with this sort of like smushed cone shape. But the actual shape doesn't matter. Our argument is going to be the same. What I'm going to do in order to estimate the surface area is I'm going to start by breaking this thing up into pieces. So maybe we start by I'm going to sketch what happens with 3 pieces. And I approximate the curve with a piecewise linear curve like so. Well, if I were to spin this piecewise linear curve, then each piece would give me what is known as a frustum. I think I'm saying that correctly. Frustum. Let me double check to make sure. Frustum, not frustrum. I'm sorry, I threw in an extra R. Frustum. And what this means really is it is a piece of a cone. So if you think about what this looks like, this is like a piece of a cone with straight sides, but they're at an angle. I hope I'm making that clear with the picture and everything here. If I were to continue the sides, they would come to a point like so. You know, this would just be a regular cone. You can also think of this frustum shape. To me, what this looks like is if you've seen one of those bowls people use to give water to their dogs, that's essentially what this kind of looks like. But that's neither here nor there in terms of what we're doing. What is the surface area of a frustum? Frustum, I'm sorry. I always add that R into there, and I shouldn't. But so what is the surface area? Well, it turns out that the surface area of one of these things, we can get this from the surface area of cones. And the surface area works out to be the average radius. So if this is my R2 and this is my R1, it is equal to the average radius, R2 plus R1 over 2. And then we use the 2 pi RL formula, just like we do for the surface area of the side of a cylinder. And so this is going to be multiplied by 2 pi. And then what is the L? Well, the L here is this distance along there. So that gives us our formula for what happens when you rotate a straight line. And if we break this up into pieces, well, then we can approximate the surface area by the sum from I equals 1 up to n of 2 pi R2 plus R1 over 2 times L. And now we got to figure out what are each of these things. Well, R2 and R1, these are actually going to be, in this particular case, they're going to be f of xi plus 1 plus f of xi. And then we're still multiplying this by L, which I had to move down a bit. But what is the length of this thing? Well, using the Pythagorean theorem, I can say, and we've dealt with that part now, so I don't really need it, the length is going to be the square root of 1 plus, technically speaking, it's going to be we have to estimate it, but it comes out to be f prime evaluated at xi squared times delta x. So strictly speaking, it's, given by the Pythagorean theorem here, but in the limit, it comes out to be the derivative. And in the limit, as n goes to infinity, this is just going to become the radius, which is just the function. So this is going to become the integral from a up to b of 2 pi times f of x times the square root of 1 plus f prime of x squared dx. And more generally, what we can say is that this is really just the radius. So if I were maybe rotating this thing around a curve other than the x-axis, I could say, in general, we're doing the integral from a up to b of 2 pi times the radius as a function of our height along this thing times the square root of 1 plus dr over dh squared integrated along the height. So the height direction is the direction along the axis of rotation, and the radius is our distance away from the axis of rotation. And this formula, then, you derive this formula in exactly the same way as we derived the one for rotation around the x-axis. So I'm not going to repeat it. It's pretty much the same argument, but this is just in general. So in our previous example here, x is our h and f is our radius, but it doesn't always have to be that way. You can get other types of formulas for this sort of thing. So as an example of this kind of stuff, we could ask, maybe we want to set up an integral for the surface area from rotating y equals e to the x about the x-axis. So how do we go about doing that? Well, we're just going to use this formula. Oh, and let's say from x equals 0 to x equals 1. Well, the answer is, to set this up, we're going to do the integral from 0 to 1, and we're going to be integrating this along x, because that's the direction of the axis of rotation. And then the radius is just going to be given by y in this case, because we're rotating it about the x-axis. So this is going to become 2 pi times y, which is really e to the x, times the square root of 1 plus y prime squared, which is going to be e to the 2x. Now, this is actually a relatively straightforward integral to solve, and the reason that this is a relatively straightforward integral to solve is because you could actually do this with a u substitution, right? So you could say, let's let u be equal to 1 plus e to the 2x, and then this is going to be, well, let's just write it out and do it, because that's probably easier. So I will show you how to do this one, since it's, we may as well see how to do at least some of them. In general, we may just set up some of these, but this one, what we can do, if I wanted to solve it, I can say, let's let u be equal to 1 plus e to the 2x. And then what we're going to have here is, oh, maybe this isn't as easy to solve as I thought it was. Yeah, I think there was a reason why I said I wanted to just leave this one as set it up. Because the problem is that when I do this, then du is 2e to the 2x dx. But I actually only have e to the x here. And that really throws things off quite a bit. Does it throw things off to the point where it is unsolved? Yeah, let's not bother trying to solve that. This is not one that I would set up to solve ahead of time. It's one that I just looked at for a moment and I was like, oh, maybe that's easy to solve. But no, that is definitely not easy to solve. So I'm going to skip solving that one. We'll just set it up. Now, let me see what would happen if instead of rotating it about the x-axis, what if instead we said we wanted to rotate it about the line y equals -2? Well, in that case, the setup, my new radius would be y plus 2. So now I would do the integral from 0 up to 1 of 2 pi times e to the x plus 2. But the derivative of the radius would still be the same as last time. So it would still just be the square root of 1 plus e to the 2x dx. And so that would give me my setup for a rotation around y equals -2. What if, on the other hand, I wanted to rotate this curve around, let's say, the y-axis? So this is the curve, the line x equals 0. Well, in this case, my height direction is going to be along y, and my radial direction is along x. So what I want to do here is I want to notice here that x is equal to the log of y. And this is now the curve that I'm going to be rotating. And this is going to go from 0 up to 1. So y is going to go from y equals 1 to y equals e. So we're going to have the integral from 1 up to e, and then we're going to have 2 pi times the radius here, and the radius in this case is going to be the log of y times the square root of 1 plus 1 over y squared. That's the derivative of the radius. And then we are integrating this over dy. Now, once again, I think this becomes a really nasty integral to actually solve. So that's why we are just setting this one up and not actually solving it. But there we go. This is how we set it up. Now, I told you I wanted to show you at least one that we work out completely. So let us see if we can do that in at least one case. So let's take a look at the following surface area question. Let's suppose that we want to find the surface area from rotating the curve y equals the square root of 9 minus x squared from x equals -2 to x equals 2. Oh, and we're going to be doing this about the x-axis here. So the setup is not going to be too bad. We're going to integrate from -2 up to 2 pi times square root of 9 minus x squared, and then we're going to be multiplying by the square root of 1 plus. Now, what is the derivative of this thing? Well, it's going to be dy by dx is equal to 1/2 times 1 over the square root of 9 minus x squared times negative 2x. So the 2's cancel and leave me with negative x divided by the square root of 9 minus x squared. And when I square that, this is going to become x squared over 9 minus x squared dx. So there we go. We've got our integral set up here. And what we can do is we can rewrite this thing here a little bit. So this looks like a very difficult integral at the moment, but this is one of those cases where actually to solve it, what we need to do is to be clever with our algebra to simplify things. So in fact, take a minute and see if you can figure out how to simplify this a little bit and maybe see what you can come up with here. All right, so were you able to figure out anything that simplifies this? The key is to look in at this term. So this is going to become, if I take a common denominator here and combine these, what I'm going to get, and we'll write down this part of the integral first, we're going to get the square root of 9 divided by 9 minus x squared when we combine these fractions. Because what is this going to become? I multiply this by 9 minus x squared, and then the negative x squared and the positive x squared cancel and just leave me with a 9. And now I have a common denominator, so this is what I have. But this is now going to become a really, really nice integral, because this is actually just going to be the integral from -2 up to +2, 2 pi square root 9 minus x squared times 3 over square root 9 minus x squared dx, and I can cancel those, and now we just have the integral of 6 pi. So this is going to become 6 pi x evaluated from -2 to +2, which should come out to be, let's see, 2 times 6 pi is 12, plus another, we get 24 pi. So there we go. We have been able to figure out this surface area exactly. But as I said, a lot of these problems are going to be rather difficult to solve explicitly. So I don't necessarily always suggest that you try to solve these things by hand, or at least don't try to solve them without access to a table of integration or something like that. Now, give me a second because I want to bring up a really cool example here that we can do. Yeah, here we go. So this is an object known as Gabriel's horn. And the object is the curve y equals 1 over x rotated about the x-axis. Now, what I want to do is I want to first start by calculating the volume of this thing. Now, the volume of this thing is actually very easy to find by using the formula for volumes, right? So, oh, and I didn't tell you the bounds, did I? So from x equals 1 to x equals infinity. So the volume here is going to be the integral from 1 up to infinity of pi r squared, which is pi times 1 over x squared dx. So this is going to be pi times the integral from 1 to infinity, x to the -2 dx. And so this is going to become negative pi x to the -1 evaluated from 1 up to infinity. And as we approach infinity, this term becomes 0. As we approach 1, it becomes 1. So this comes out to be pi. So this thing actually has a volume that is just pi. So it has a finite volume. But now let's write down the surface area of this thing. And in fact, what I would like for you to do is I would like for you to try to calculate the surface area yourselves before you watch me doing it. on the board for you. So pause this, take a minute, and try it out yourself. Okay, were you able to find it? Did you find something interesting that happened? Well, the surface area is going to be given by the integral of 2 pi times 1 over x times the square root of 1 plus, now the derivative of this thing is going to be negative 1 over x squared. So this is going to become 1 over x to the 4th dx. Now, this is going to be a little bit of a mess for what's going on here. But here's what's going to happen. And I don't necessarily expect you to have figured all of this out, but I thought it would be a good exercise for you to take a minute and think about this a bit. I can rewrite this as, or I forgot the bounds, didn't I? This should be 1 up to infinity. This is going to become 2 pi times, on the inside here, I get x to the 4th plus 1. So we're going to have the integral from 1 to infinity. I'm going to have 1 over x times the square root of x to the 4th plus 1 divided by x to the 4th dx. So this is going to become 2 pi times the integral from 1 up to infinity of square root x to the 4th plus 1 divided by x cubed dx. And now, here is what we can say. We can see that this quantity in the top is always going to be a little bit bigger than x squared. So what I can say is that for x bigger than or equal to 1, the square root of x to the 4th plus 1 is bigger than or equal to x squared. So that means my integral is going to be bigger than or equal to 2 pi times the integral from 1 up to infinity of x squared over x cubed dx. But this diverges to infinity. Why? Because this is the integral of 1 over x. We know how to do the integral of 1 over x, and that comes out to be infinity here. So what that means is that if this integral diverges. So what this means is that the surface area is infinite. We have an infinite surface area, horn shape, but it only has a finite volume. That's really interesting. So it contains a finite volume even though it has an infinite surface area. Now that seems weird, and I want to talk about the weirdness and also talk about where we've seen similar kinds of things, okay? So first of all, this is not the first instance where we've encountered something weird like this. If you think about the region under y equals 1 over x squared, from 1 up to infinity, that looks like this. Now, what is the arc length of this curve? Well, the arc length is going to be infinite because the arc length is certainly going to be bigger than the length from 1 up to infinity along the x-axis in a straight line. So the arc length is infinite, but this region comes out to have a finite area. So this is sort of a two-dimensional analog of what we just found. This is a region that is infinitely long, but it has a finite area. Well, we just found a volume that is a finite volume, but an infinite surface area. It's the same kind of thing, though. The same sort of thing going on. But this does seem a bit paradoxical, because if we think about it, one way that people sometimes talk about this Gabriel's horn thing, so let's write down what we found. Y equals 1 over x rotated about the x-axis from x equals 1 to infinity has finite volume, infinite surface area. And one of the things that people say about this is, well, that means that if this were a physical container, it can only contain a finite amount of paint, but you cannot cover the surface with a finite amount of paint because you've got an infinite surface area. How can you cover an infinite surface area with a finite amount of paint? And yet this thing only holds a finite amount of paint. Yeah, but they're making a mistake here. It sounds like a paradox, but it's not. And here's the reason. The way that it only holds a finite amount of paint is because as you go down the tube, let me draw a picture of this tube up here. As you take this 1/x curve and you rotate it, right, you do get this horn shape. But as I go down here, this is getting thinner and thinner. So the reason it contains an infinite volume or a finite volume of paint is because to fill this thing with paint, to get all the way down to the end, so to speak, I have to allow the paint to occupy a smaller and smaller radius. Normally, when we say that you cannot cover an infinite surface area with a finite amount of paint, we are technically lying. You cannot cover an infinite surface area with a finite amount of paint if you require that the paint on the surface remain of a certain thickness. Like normally, people think of spreading paint as a two-dimensional task. It's actually three-dimensional. The paint has a thickness. If I allowed my paint to get down to an infinitely small thickness, then I could in fact cover an infinite surface area with a finite amount of paint. So yes, you can cover an infinite surface with a finite amount of paint. In fact, you can cover the entire plane with a finite amount of paint if you allow yourself to let the paint become infinitely thin. Now, physically, that's impossible because paint is made of molecules and molecules have a minimum size that they can be. But we're talking about abstract, idealized paint. So actually, the solution to this paradox is that you can cover infinite surface area with finite amounts of paint as long as you don't require that the paint be spread with a certain minimal thickness. Okay, so this is, I think, a very cool example of surface area stuff and whatnot. So, again, these are very difficult problems to do in general. And in fact, to find a good problem to show you, I must admit today I actually did take an example out of Pal's online math notes and just kind of do the same example. What I would like for you to do is to practice the other examples on his notes and see what you can do. You know, I keep using his notes. The reason is because I figured there's no reason to reinvent the wheel. I could write up some problems for you to do, but if somebody's already got them for me, I'm not going to do it again. I'm just going to point you in their direction. But I'd like you to take a look at his other example and his practice problems and try to figure out how to do those. Let me know if you run into any difficulties with that. And again, remember that a lot of the thing that I want to focus on here is how do you set up the surface area integral? Because in practice, in the real world, if you were doing something like this, it would probably suffice to just say, oh, we just need an estimate. We can either solve this by computer, or we can maybe even just use a numerical estimate by computer to get our surface area. We don't need a precise answer. So setting up the integral is usually the most important part. And next week, we will delve into some additional examples of stuff you can do with integration.